We will continue talking about aerofoil aerodynamics. In the previous 3 modules, we talked about the basics of aerofoil theory, what is lift coefficient, what is drag coefficient, what is the pressure coefficient, and so forth. We also talked about the power of scaling, that rather than dealing with lift and drag as dimensional quantities, we always like to deal with non-dimensional quantities, because it's easy to scale from a very small scale model to a large scale aircraft or a large scale wind turbine. In the second part of module 3, we talked about the potential flow equation, we talked about vorticity, velocity potential, and so forth. In the third part of it, we dealt with panel method. We showed you how a panel method works, and we gave some examples of it. The panel methods basically deal with inviscid flow, which is just the outer flow outside the boundary layer. You may remember that near the wall there is a boundary layer. In the panel method, we have collapsed that boundary layer into a vortex sheet, and what we are doing was solving for the strength of the vortex sheet. So now we turn our attention to boundary layers, because without knowing what's going on in the boundary layer, we cannot compute the drag. So panel method gives the lift. To compute the drag, you need some kind of a boundary layer analysis. It could be done in a number of ways. In many of the commercial programs and also public domain programs, such as X-Foil, this is done using some simplified empirical approaches. So we briefly review these empirical approaches in this module. So we're going to look at computing the laminar flow. You may recall in our previous module we said that if there's not a lot of mixing, eddies, currents, and so forth, the only mixing that takes place is molecular mixing from one layer of the fluid to the other layer of the fluid. So those type of flows are called laminar boundary layers. Lamina means layer, so its flow is going layer by layer. There's very little communication between one layer of fluid and the other one, except through a random molecular diffusion. You could visualize it as a 2 pile of students walking on a group of students walking. So from one pile to another one, somebody randomly jumps in or jumps out. So very slowly mixing is taking place. At some point in the flow, however, the flow becomes turbulent. So where does it go from laminar to turbulent is determined by a process called transition. There is a separate module that deals with what is transition, what are the physics behind it. We will not cover it, but it's there in your textbook, ebook, and also in the other places. So we'll just give you the empirical relationship that tells us when you go from laminar to turbulent, what happens. So once you go to the turbulent flow, you need to use different type of empirical relationships. So there's a technique called Thwaites Method, which is often used in many computer programs. So you compute the laminar flow, determine where the flow becomes turbulent, then we switch over to turbulent flow. Once you have completed this, when you reach the trailing edge of the aerofoil, you look at the properties of the aerofoil, such as boundary layer, such as how thick is the boundary layer, what is the skin friction, and so forth. Then we can compute the drag. So there's a lot of background material on it. It's given in the appendix of our ebook, all these properties. Today we just show the mechanics of how this is done. There are a number of computer programs such as X-Foil, Pablo, Java Foil, and many other programs that will do this job. So today we just describe the process. We may show how such a program works in a later slide. So what's Thwaites method? This is a method developed by this particular author. He did not even write a paper. Just in a book in 1960, he described this method. He said he looked at a lot of boundary layers over aerofoils, flat plate, channels, and all kind of things. Then he found that a quantity called the momentum thickness, which is a measure of how much momentum is lost in a boundary layer, because of the viscous effects could be written as this. Here nu is called the kinematic viscosity. Kinematic viscosity is the molecular viscosity divided by the fluid density. This is the edge velocity gradient outside the boundary layer. So when you do the potential flow, you basically get this quantity, so all over the surface. So if you take a streamwise derivative along the surface, you get this expression. So he came up with this relationship. Again, this is edge velocity is what we used to call gamma in our panel method. This is the kinematic viscosity. So he found that this forms a nice straight curve fit, and the intercept was a equal to 0.45 and the slope was 6. This was his best fit. So he integrated it analytically. All you have to do is put 6 here, bring it over the other side. You see UE times theta squared, and you have theta squared times UE. So you could use what we call the separation by parts or a product rule. So we could come up with a combined expression. That expression looks like this. When you integrate it, you get some values, constant of integration. That constant of integration works out to be 0. We are not describing the details here. So basically the boundary layer momentum thickness growth is given by this particular relationship. So for blunt aerofoils, as well as the flat plates, this relationship still holds. So all you need to know is what is the potential flow velocity from a panel method. You can raise it to the power 5, then integrate along the surface, starting from the nose of the aerofoil at the stagnation point all the way to a current x location. Then you get the square of the what we call the momentum thickness. Once you have the momentum thickness is found, you could find an empirical quantity called shape factor. We will describe these quantities in a separate slide later on. So you could solve for the shape factor. Shape factor depends on a parameter called lambda, which again involves the momentum thickness squared. This is the kinematic viscosity. This is the x gradient, or the gradient along the aerofoil surface of the outer potential flow velocity. This is same as the gamma that we found earlier. Once you have the lambda, depending on its sign, whether it's a positive or negative, you compute a quantity called shape factor. Once you have it, you could also compute the skin friction. Skin friction is the shear stress of the wall. This is what causes the drag divided by dynamic pressure at the edge of the boundary layer. So as soon as you have the lambda, you can solve for the skin friction. Recall the lambda is given in here. This is coming from the potential flow. This is the property of the fluid. This is the momentum thickness squared, which comes from this particular equation. Sounds awfully complicated, but if you look at a program such as Pablo, all of it is in a very, very small loop like this. No more than perhaps 20 lines, 15 lines. We would find the empirical relationship for shape factor, lambda, CF. You would see things like something raised to the power 5. That's where we are integrating and all these things. There's some extra things here. We test the flow to see whether the flow became laminar to turbulent. So how do we do it? This is before we do that, this is the relationship for H in terms of lambda. This is nothing more than the equation that we saw here cast as a MATLAB code. So if you know the lambda, you can solve for H. So in the previous notation, that's what we are doing. So we are solving for the lambda in terms of, once you know lambda, you can solve for H. Likewise, if you know lambda, we can solve for shear stress of the wall. Then you can solve for the skin friction. So skin friction is given in here. All these steps are just the empirical relationships that we saw earlier. How do we go from laminar to turbulent flow? Many approaches are available. For laminar, for wind turbine aerofoils, there's a method by a person called Epler. For aircraft, there's an empirical method called Michel's method. So I'll just show an example of one of these methods. There's a lot of reports available. For wind turbine applications, people normally use Epler's method, but I will show the Michel's method just as an example. In the Michel's method, you first compute the momentum thickness using Thwaites method. This is the theta squared, take a square root of it, theta, multiply by the edge velocity, then by kinematic viscosity nu. This is a non-dimensional quantity. This is called the Reynolds number based on the momentum thickness. You also compute the Reynolds number based on the distance from the leading edge. So as you march from the leading edge, as you compute this theta, keep track of where you are on the aerofoil. This is the distance from the stagnation point near the nose to where you are on the aerofoil. So once you have these two expressions, check this. If this number is larger than this number, then you have become turbulent. So that's what we are computing here. So if RET, which is this number, Reynolds number based on the theta, is larger than RET max, which is this number, then the flow has become transition. So we have become turbulent. Once you have become turbulent, you need to use another empirical method. Thwaites method no longer works. So there are lots of approximate methods available. Many programs use a technique called Head's method. This is available in Pablo, Xfile, Java file, and many other programs. So Head's method, you solve an ODE, ordinary differential equation, for the growth of momentum thickness in the turbulent flow, starting from the transition location. This is a first order ODE. This is the edge velocity or the potential flow velocity. This is the skin friction of the wall. There is a new empirical parameter called H1 is defined. This is the boundary layer thickness minus displacement thickness by momentum thickness. So these parameters may not be familiar to you. There are some resources at the back of the book that define each one of these. For now, this quantity is also empirically modeled. So again, this is an ordinary differential equation. MATLAB is very good at marching from the transition location to the trailing edge of an aerofoil. You could just march. So you march, solve for H1. Once you have H1, then you solve for H, or vice versa. Then once you know H, you solve for the skin friction. Once you have the skin friction, you put it in here, H in here, march to solve for theta. So there's one ODE that you march from left to right, from the transition point towards the trailing edge. This is another ODE for H1. All the rest of it is empirical relationships. If H1 becomes very, very high, like 3.3, then you say, my flow has separated, I'm going to stop. So we do not use it above that value. It sounds awfully complicated, but again, in a MATLAB code, just a few lines of code is all it takes to program all of these things. Once you have all of these, then how do you find the drag? The drag is due to boundary layer growing on the upper surface, boundary layer going on the lower surface. This formula is called a Squire-Young empirical formula. Once you know the theta, the trailing edge, from the Head's method, divided by chord, make it non-dimensional distance. Trailing edge velocity, this is from panel method, non-dimensional by free stream, so again a non-dimensional number. Then 5 plus the shape factor h at the trailing edge divided by 2. So do this for the upper and do similar thing for the lower, add it together, you get the drag coefficient. So this is how many of the computer programs work. They compute the drag coefficient. Therefore, the panel method is used to compute the lift, and then some kind of an empirical relationship used to compute the drag. So this is how these things work.